Welcome back to the deep dive. Ever stop to think about how electricity actually gets made from spinning things, or how motors drive, well, almost everything?
Yeah, it pretty much all comes down to AC machines.
Right, these amazing devices that convert mechanical energy into AC electrical energy that's your generator.
You can flip it around, AC electrical into mechanical, that's the motor.
And the core principle behind it all is electromagnetic induction, isn't it?
Absolutely. Now, within AC machines, there are really two main players,
Mhm.
synchronous and induction machines.
Okay, synchronous and induction, what's the big difference there?
Well, it's mostly about how the rotor gets its magnetic field going. Synchronous machines, they need a direct feed, like a DC current.
Okay, direct current needed.
But induction machines, they're pretty clever. They actually induce the current in their own rotor, kind of like a transformer does. No direct wiring needed for the rotor current.
Interesting. So today we're going to unpack the basics first, then look closer at both induction and synchronous types, as motors and generators.
Sounds like a plan.
And here's a cool fact to start. Take a simple two-pole AC machine. One full spin of the rotor gives you exactly one cycle of AC power.
Right, one mechanical revolution, one electrical cycle. Simple.
But if you make it a four-pole machine, that same single mechanical spin suddenly gives you two electrical cycles.
Exactly. It doubles the electrical output frequency for the same physical rotation speed. It's all about the poles.
So there's a direct mathematical link, right?
Yeah.
Between the mechanical rotation and the electrical angle or frequency.
Oh, definitely. The electrical angle is just the mechanical angle times half the number of poles. And the frequency. That's tied directly to the number of poles and the rotational speed, the RPMs. The formula is F equals P times N over 120.
P is poles, N is RPM.
Got it. So designers use this to hit specific frequencies, like 50 or 60 hertz.
Precisely. Now let's talk about the windings, specifically the armature windings where the AC current is generated or used. The big goal is usually getting a nice, smooth, sinusoidal voltage waveform.
Okay, and there's specific jargon for how these windings are put together. Yeah, a bit. You've got the actual conductors, the wires in the slots doing the work. Two conductors make a turn, a bunch of turns make a coil.
Coil sides sit in the slots, right?
Yep. And then there's pole pitch, basically the span of one magnetic pole, usually measured in slots, like 36 slots and 4 poles means 9 slots per pole. That's 180 electrical degrees.
And the angle between slots.
That's the slot angle. For those 9 slots per pole, the slot angle would be 180 divided by 9, so 20 electrical degrees.
Okay, so it's all very precisely laid out.
Hmm.
I also heard about short pitch and distributed windings. What's that about?
Right, good point. So instead of making a coil span the full 180 electrical degrees, the full pole pitch, you can make it slightly shorter. That's short pitching.
Why do that?
Well, it actually helps clean up the waveform, reduces unwanted harmonics, makes it more purely sinusoidal. Plus, it uses a bit less copper wire. The downside is slightly lower voltage output.
And distributed.
That means instead of bunching all the coils for one phase together, you spread them out over several slots under a pole. Again, this helps smooth out the voltage waveform.
Makes sense. It's like fine-tuning the output. So all these design choices, short pitching, distributing the coils, they affect the final voltage.
Absolutely. We use something called winding factors to quantify this. There's a pitch factor, KTP, for the short pitching, and a distribution factor, KD, for spreading the coils out.
KP-KD.
Yep. They both tend to be slightly less than 1, meaning they reduce the voltage a bit compared to a theoretical ideal winding. But the overall effect, the winding factor, KW, which is KP times KD, gives a much better quality waveform.
And this K feeds into the main voltage equation.
Exactly. The induced voltage per phase is about 4.44 times the magnetic flux per pole, times the frequency, times the number of turns per phase, all multiplied by that winding factor, Kw.
Okay, that ties the design to the performance neatly. Let's switch gears to motors. Induction motors, you said they're super common.
Oh yeah, they're the real workhorses. Think of them like a rotating transformer. Power the stator, it creates a rotating magnetic field,
Which then induces current in the rotor.
which creates the rotor's own magnetic field, and bam, it starts chasing the stator field. Torque.
And the big advantage is no direct electrical connection needed for the rotor.
That's a huge part of it. It makes them simple, rugged, reliable, pretty cheap, easy to maintain, and usually quite efficient.
Any downsides?
While their speed isn't perfectly constant, it drops a bit under load. Starting torque isn't always massive compared to some other types, like DC motors, and they tend to draw a lot of current when starting and operate at a lagging power factor.
You mentioned slip before. That sounds important for these.
Crucial. The rotor never quite reaches the speed of the rotating magnetic field, the synchrony speed. That difference in speed is the slip.
Why is slip needed?
Because it's the relative motion between the rotor conductors and the rotating field that actually induces the current in the rotor. No slip, no induced current, no torque.
Ah, okay. So the rotor has to lag behind, it has to slip, and the amount of slip depends on the load.
Exactly. More load means the rotor slows down a bit more, increasing the slip, which induces more current and generates more torque up to a point. The synchronous speed itself, ends, is just set by the frequency and poles 120 times F over P.
And the frequency of the current in the rotor, is that the same as the supply frequency?
No, it's actually the slip times the supply frequency. So
Yeah.
if you have 5% slip on a 60 hertz system, the rotor current frequency is only 3 hertz. Very low.
Fascinating. So what about the torque they produce?
Torque depends on things like the rotor current, the strength of the stator's magnetic field, and the rotor's own power factor. There's a specific point, a specific slip value, where you get maximum torque. Interestingly, the value of that maximum torque doesn't depend on the rotor resistance, but where it occurs, the slip value does.
So you can shift the peak torque point by changing rotor resistance.
In some types, yes, the wound rotor or slip ring motors, not in the common squirrel cage ones, though.
And these motors can operate in different ways.
Right. Normal motoring is when slip is between 0 and 1. If you force the rotor faster than synchronous speed, slip becomes negative, and it acts as an induction generator, pumping power back to the grid.
Oh, interesting. So it can generate too.
Yes, but it needs the grid to provide reactive power to establish its magnetic field first. And if slip goes above 1, meaning the rotor is spinning backwards relative to the field, it acts as a brake.
Motoring, generating, braking, very versatile.
Yeah.
How do we usually start them, given that high starting current issue?
For smaller ones, sometimes just direct online connect it straight to the power. For bigger ones, methods like star delta starting or using an auto transformer reduce the initial voltage and current surge. For slip ring types, you can add resistance to the rotor circuit temporarily during startup.
Okay, lots of options. Now, what about the other main type, synchronous motors?
Ah, the synchronous ones. They are precision machines. Once running, they lock onto the supply frequency and run at exactly synchronous speed. No slip.
Perfectly constant speed. That sounds useful.
Very useful for certain applications. And they need that external DC supply for their rotor field. A big advantage is they can be made to operate at unity or even leading power factor, which can help improve the overall power factor of a plant.
But they're not self-starting, right? Unlike induction motors.
Correct. The rotor has inertia, and the stator field is already spinning at full speed instantly. The rotor poles just get pushed back and forth and can't lock on from a standstill.
So how do you start them?
Couple of ways. You could use a separate pony motor to bring it up to near synchronous speed, then energize the DC field, and it should pull into sync.
Like giving it a push start.
Kinda, yeah. Or you can sometimes start them using a variable frequency drive, slowly ramping up the frequency from 0. A very common method, though, is to include damper windings in the rotor poles, basically a squirrel cage structure.
Ah, so it starts like an induction motor.
Exactly. It uses the damper winding to accelerate close to synchronous speed, and then you apply the DC field, and the main rotor poles lock in with the stator field.
Clever. So induction motors are the rugged generalists. Synchronous are the precise speed specialists.
That's a pretty good summary. And when you run a synchronous machine as a generator, which we usually call an alternator, that's how most large-scale power generation happens.
Driven by a turbine, the rotating DC field on the rotor induces AC in the stator windings.
Yep, Faraday's law in action. And you control the output voltage by adjusting that DC field current. Induction generators, as we mentioned, are also used, especially in wind turbines, but they have that different characteristic of needing reactive power from the grid.
Right. So we've gone from basic principles through winding designs to the nitty-gritty of induction and synchronous machines, both motors and generators. It's quite a journey, but it all connects.
It really does. These machines are just everywhere, underpinning so much of modern technology.
Absolutely. And thinking about the future, here's something maybe to chew on. As we rely more on renewables like wind, which often use induction generators, how does their need for reactive power and their sort of follower nature compare to the traditional grid built around synchronous generators? What challenges or maybe opportunities does that create for grid stability and control?
That's a really critical question for the energy transition. Definitely something engineers are grappling with right now.
Food for thought indeed. Thanks for exploring AC machines with us today.